how did we get 2 positive charges here and multiply that by 2? We have a total of 4 positive charges. Everybody with me?
Mm-hmm.
It must have involved a loss of 4 electrons. Those 4 electrons are someplace in cyberspace here, floating around, waiting to go home someplace. It's looking now for Juliet. All right? So this is the reaction we want to get. Now this must be Juliet because they're the only 2 guys living on that side of the highway. This is the highway. It's the 2 guys that live on this side. So those are the ones that are going to get together, and oxygen is going to be the next candidate. So we call the loss of electrons, is called an oxidation. Okay? And you say, well, how am I going to remember that? Well, just remember the word oil. Oil, oxidation is a loss of electrons. Right? All right? So let's look at the next step. If there's an oxidation, it must have a partner. And that partner is called a reduction. A reduction in this case, since the only other people living on this side of the street are magnesium and oxygen must be the other partner. And I want you to look at the charges now. This started off as O2. O2 is neutral. If it gathers up 4 electrons, it's going to break this down into 2 oxygens. Each one has a negative 2 charge. 2 oxygens, each one has a negative 2 charge. Add them together, negative 4, right? There were 4 electrons here and 4 electrons here. If this is the product of this reaction in red, 4 electrons is the product, that product is used as a reactant in the next step. All right, you see how they go together? Oxidation and reduction involve the same number of electrons. So therefore, what did we learn just from this little simple exercise? We learned that equations must be balanced several ways. They must be balanced. They must have the same number of atoms on both sides. You see it? 2 magnesiums, 2 oxygens. They must also have the same types. There's no chlorine here. There's no sodium. There's nothing but magnesium and oxygen. Magnesium and oxygen, magnesium and oxygen. So the same type and the same number of atoms on both sides. What else did we learn? They have to have the same mass on both sides, right? We know all of that. They must also have the same charge on both sides. The charge at the moment, this has no charge, you see it? And this has no charge. So nothing here is charged, and that's okay. 0 charge is perfect. The thing is that you can also have the same charge. That means that both sides of the equation could have 2 negative charges. Negative 2 on one side and negative 2 on the other. Positive 6 on one side, positive 6 on the other. It depends on how the reaction is written and what's involved in the reaction. This is a very simple reaction. So the next step here is to say if one is oxidation, what would be the oxygen? The oxygen must be reduction, all right? So oxidation is a loss of electrons. Reduction is a gain of electrons, and we say our oil rig. You've heard of the word oil rig? Oxidation is a loss, reduction is a gain. I frankly think that's too much to remember. All right? What I like to look at is something called oxidation numbers. This is the more universal way of thinking about oxidation and reduction. An oxidation number is the charge on the atom. We've already learned that. We know the periodic table. I know what the charges are, right? So I don't have to memorize anything. I'm good. I know the charges. So if I'm working with aluminum, all right, I know the charge on aluminum is 3 plus, right? I know the charge on sulfur in a chemical reaction would be 2 minus, okay? These are called charges, all right? The charge means it already lost 3 electrons. Is that right? That gives me the privilege to write a 3 plus. That means it lost 3. What does this mean? Gain. That means it gained. That means it's finished. The reaction's done. It already gained 2 electrons. Yes?
I have a question. In the table, on CN reaction, it doesn't have these oxidation numbers, but the limits.
Oh, those are, I'll show you that in a minute. That's what I'm talking about. Let me get there. So we know what charge is. Charge is a finished product. If you gain 2 electrons, you got 2 negative. If you lose 3 electrons, you get positive. Are you with me on that? Now, we have to think in terms of past, present, and future, all right? When I tell you I have this charge, what does that mean? I'm talking about the past, it's over. This has already lost 3 electrons. When I talk about this, what am I saying? It says gained, right? Now I'm going to write this differently. Now I'm going to write oxidation numbers. These are called charges. These are charges, right? Charges are, you know what they are. I'm going to write an oxidation number for aluminum. You ready? Do you see the difference? What's the difference? The plus sign location.
Oh.
See the plus sign location? Where's the plus sign here? This is in front?
Yes.
This is behind. So therefore, if that's the oxidation number for aluminum, that must be the oxidation number for sulfur. Now, oxidation number is, remember I said past, present, and future, right? That's future. It's saying the behavior of aluminum is that it could lose 3 electrons. It didn't lose it, I'm just talking about it. I'm just saying, aluminum can lose 3 electrons. I'm just saying. I'm not having it happen. I don't care if it happens. I don't care if you want it to happen. It hasn't happened yet, but it can happen. So this oxidation number is behavior. This is how it's going to behave, right? What is this? What is this going to be? This already happened. It's too late, right? Too late. The behavior is, I like hamburgers. I like pizza. What is this all about? I ate the hamburgers and I ate the pizza. It's too late. It's gone. It's in my belly. Yes.
Vice versa.
Huh?
The one that's soft is the one that's not.
The one that's been happening, we've been talking about ever since the beginning of the semester. That's the chemistry we've been talking about. We always talk about a charge. Now we're talking about behavior. We're saying that aluminum can lose 3 electrons. Now getting back to what you were saying here, oxidation number and charges are related only in a few instances. Column 1 and column 2 always have oxidation number and charge are exactly the same. So if I ask you what's the charge on strontium, you would say 2 plus. Strontium, second column. If I ask you what's the oxidation number of strontium, you would say plus 2. Just switch the charge, all right? Now, aluminum, zinc, and silver, I told you this earlier, they always have the same oxidation number and the same charge. Everything else on the periodic table is variable, except for the noble gases. They never react anyway, so who cares, right? So only those 2 elements on the periodic table, column 1, column 2, and aluminum, zinc, and silver. They all have the charge is equal to so the charge is equal to the oxidation number, all right? But in most cases, that's not true. Remember, the periodic table has 114 elements. Only about, less than 15 elements. In that case, it's true, all right? So let's just show you what we're talking about. Chlorine, you asked about chlorine, all right? So I want to look at chlorine. First of all, I'm going to show you how to look at chlorine in a very simple model. This is sodium chloride, right? To understand oxidation number is like money in the bank, right? You want to go and find out how much money you got in the bank. You go type up your name. You get up on the screen comes all your records, and you know how much money you have in the bank. Okay? You know how much money potentially you could spend in the future. Am I right? So it's like money in the bank. So then why don't we use an accounting method? This is accounting. This is not chemistry. Accounting looks at what's called a T-table. Has anybody taken accounting in this class? Okay, I can lie to you then. This is a T-table. No, this is a T-table. And what I know about the T-table is if I go to the periodic table, I can find out what the oxidation number is of chlorine. Right? What is the oxidation number of chlorine? Right now, in this particular case, I've been working with this a long time. I'm going to give it a -1. All right? Now, if I was going to write the charge on chlorine, what would I put?
1.
No, I'd leave just minus. I wouldn't put the 1. Right? Now, again, because we're talking about banking and accounting, if I go up to the teller and I say I want to have a minus, What's the teller gonna say?
Minus one.
Minus what? What are you gonna do? You're gonna withdraw money? Well, tell me how much you wanna withdraw. Oh, minus 6. You know, the minus goes in the front.
Yes.
Right? I wanna withdraw 6. So you need to have a number when you're talking about accounting. That's a number. I wanna withdraw $1. Stupid, but I wanna withdraw $1, right? If this is 1, now I wanna show you how this works. I don't know the oxidation number on sodium. I'm lying. But I don't know what the oxidation number is on sodium. So what I'm going to do is I'm going to then use this T-table and say, well, if this is minus 1, the entire bottom of this table has to be equal to 0, because that's a neutral compound. Therefore, for this to be 0, and this is minus 1, this must be plus 1. I then carry the plus 1 up here, and I've just solved the problem. I know what the oxidation number is of sodium. On the test the other day, I gave you a compound which was WO3. Many of you got, I'm not finished correcting your papers, I'm just doing it, I'm almost through. I gave you WO3. The question is, what's the oxidation number on W, on tungsten? What am I doing? To the T-table, I separated the metal from the non-metal. Oxidation, oh, by the way, oxygen always has an oxidation number of minus 1. That's oxygen. Oxygen always has 2.
Yeah.
And this always has a charge of 2 minus, right? That's a charge. This is an oxidation number. Got it? So I'm going to use the minus 2. I'm going to complete the T-table because I need to make a sum down here. This is going to be 2 times 3 minus 6. This has to equal 7. What's the charge on tungsten? Plus 6. Plus 6 is the oxidation number, not the charge. It's an oxidation number. Does you see where the plus sign is?
Yeah.
It's in the front. All right? Now let's talk. All right? So you have, we just learned that chlorine can have an oxidation number of minus 1, right? Okay. So now I want to take something that I'm familiar with, HClO. This is hypochlorite. Hypochlorite is found in Clorox. This is the active ingredients in Clorox, right? Now what I want to do is I want to find out what is the oxidation number on chlorine. You know, could it have a charge? Could chlorine in this particular instance have a charge?
Yeah.
No, it can't have a charge because there's no metal. Only metals can transfer electrons. There's no transfer of electrons here. This is a covalent compound. This, what I told you here, was just an example. This I knew already, the charges and the oxidation numbers are the same. I knew that because that's a metal. It comes from column 1. I told you already, column 1 has a true charge and an oxidation number are the same. This is very doubtful. I don't know what it is. So what I'm going to do, I'm going to do a double T-table. And I like to call this one tic-tac-toe. You know what tic-tac-toe is?
Yes.
All right. And now I'm going to do a little analysis. I told you that oxygen always is minus 1. I'm sorry, minus 2. I keep saying minus 2. Hydrogen, I know, is another one. Why? It's in column 1. See, it's in column 1. Therefore, I know that it is plus 1. Not 1, plus 1. And now what I want to do is I want to find out what is the charge going to be if this is all 0. So minus 2, this is plus 1. Therefore, the chlorine has to be what?
Minus 1.
Plus 1. Could you imagine chlorine with a plus 1?
No.
Well, it happens. What did we have over
Yeah,
here?
we have a second one.
You have a plus 1?
Yes.
You got a plus 1?
Yes.
This would be an example of a plus 1 chlorine. Now, this is the thing that's very critical. When you're doing oxidation reduction and you're working with oxidation numbers is not reality. Remember, it's accounting. We're just trying to find out what is a possible behavior of chlorine. More importantly, from this double T-table, you can answer a question. The question is, who has the electrons? In that compound, HClO, who has the electrons?
Oxygen.
Oxygen. Are you surprised?
No.
Oxygen should have the electrons. It always has the electrons. It's always minus 2. All right? So
It's
it's-
more reactive.
What's that?
It's more
It's more reactive than anything else there. It's the most reactive of the group, so therefore it's gonna take the electrons, okay? So that's why I'm saying you should not be surprised. So let's go here. Let's go to HClO2. All right, now this is going to be, this is called hypochlorite, this is called chlorite. This is just simply chlorite. This is hydrogen chlorite, or what we call chlorous acid. So I'm gonna do the same thing. A little tic-tac-toe, guys, here we go. Tic-tac-toe, -1, +1. This is gonna be +2. I keep doing -1, my goodness, I don't know why I'm doing that. This is +4. This is what, +1? The whole bottom has to equal 0. This must be, is that plus? What? I can't add. This has to be +3. +3? There's no +3? +1, -1, +5, okay, that's fine. Let's go to the next one. This is now HClO3. This is called chloric, not hydrochloric, this is chloric acid. This is very common, by the way. Chloric acid is used in industry to bleach textiles. When they make huge quantities of textiles, this is a very good compound. This is chlorine. This is called chloric acid. Now let's do this -2 times this is -6. Bottom has to be equal to 0. And this is going to be +1, +1. What does this have to be? +5. So here we have, this is +3, this is +1. So now we have chlorine exhibiting +5, +3, +1, -1. So the question here is that you have to understand, oxidation numbers are not real, they're just behavior. This is how this compound will behave in the presence of oxygen. This element will behave in the presence of oxygen. Depending on how much oxygen, who's got the electrons here? Oxygen's got 6 of them, right? It's busy sucking up electrons, that's its job. Yes?
So the only time the negative count is when you multiply? Okay, what I'm saying is, you're saying it has to equal to 0, and you have 1 plus 1, and then you have -2. So what I'm saying is that the -2 that you multiply by,
Yeah.
that's the only time the negative count.
No, the positives count also. I'll show you, let's go.
Do you understand what I'm saying? Because you're adding 1 plus 1, right?
1 plus 1
Oh,
plus -2.
oh, yeah,
Plus
okay,
1,
no, I
plus
see,
1,
I
this
see.
is +2,
I see.
and minus, they cancel.
I didn't see from here.
Plus,
but,
yeah,
you know.
that's why I was gonna do one over here for you, all right?
Yeah.
I thought that was the case, because it's just simple arithmetic. So let's try something else. Let's do potassium chromate. Potassium chromate is a very bright orange, beautiful colored material. It's extremely corrosive, this material. It's used in making original glassware. So if you look at a glass factory, they're pumping out these glasses that you would, drinking glasses at home, you know, they make millions and millions of these things. But when they make them in a mold. The mold has inside the mold, there's a release agent, so you can get it out of the mold. Otherwise, it's going to stick to the mold and it's finished. So the glass goes in there, a big blob of glass goes in, they push down on that with a piston, the glass flows all over the place, and they end up with a dirty glass, but it's a glass, okay? Nevertheless, that glass then is clean. They clean it in this solution. This solution will take away anything except glass. It doesn't react with glass. So it's extremely corrosive material. This is potassium chromate. So let's start. This is the double, this is called the tic-tac-toe. Help me out on this. -2 here, times 4, -8. We know potassium is first column, so therefore this has to be +1. This is K2, so K2, yeah, K2, this is the, now this, see this is what I thought you were talking about.
Yeah.
See now 1 times 2, this is now a +2 over here. So therefore, if this whole bottom must be equal to 0, what is that whole here? This has to be +6. Right? If you look at chromium on the periodic table, number 24, how many oxidation states do you see for chromium? Number 24.
Right here. You have 2, 3, and 6.
2, 3, and 6. That's the 6.
This is it.
See the 6? What is it here? This is -1, this is -3, this has to be +3. Do you have a +3 over there?
Yes.
Right? So she has a periodic table where there are listed a number of different possible oxidation numbers. It lists possible oxidation numbers for each and every element, is that right? Each box has got a series.
Yeah, each
all right?
box has a possible oxidation.
So this would be chromium. Chromium has a +3, it could have a +6, all right? Various oxidation states. Now notice who chromium is sitting with. Oxygen. Where are the electrons?
Oxygen.
Are you surprised? Oxygen is sucking anytime it gets near something. In fact, it's taking so many electrons away from chlorine that this thing has been completely behaving now as a non-metal. Even though it's a metal, it has so many electrons have been taken away, that's behaving as if it's a non-metal. Manganese does the same thing. Okay, MnO4. This is also a very corrosive material, not nearly as bad as this one, but this is very corrosive. It's a very strong agent. And nevertheless, we have here -2, -8. This would be +1. So what is this one going to be? This has to be a +7 for this to be equal to 0. Got it? Now let's do something that's very familiar to you guys. It's called methane.